Hello to everyone missing class. All right. We're going to start with the code we had previously written, drop with air while. Okay. And we're going to convert that into our projectile motion code with air resistance. It's because of the air resistance, we need to do time stepping. So let's start, since we're going to do that, let's first change the name of our code and call it projectile with air. We won't do with air while, it just gets a little too long. All right. So this is we'll change it, instead of a dropped object, this has become a projectile with air resistance. Okay. And this is going to stop when we reach the ground. We're going to make this more sophisticated in the future, but for now, we'll just stop when we reach the ground, or if we run out of time. Okay, so as we go down our parameter list, so since we changed the name of this, what should we do? Save as. Okay, so this is going to be projectile with air. Okay, so we now have new code that we're writing. We haven't really done anything to it yet, except change the opening comment. So let's continue throwing. Actually, a 5 kilogram mass is a lot to throw. Let's change that to a 1 kilogram mass, which is still pretty heavy. So that's a good chunk of metal. It's a brick. Okay. And we will have, we'll keep time at 10, T max at 10. Okay, we'll keep our time steps at 0.1. We may want to bring that down in the near future. Now we're going to need, if we have a projectile, we need an initial velocity. We can keep that at 40, but what else do we need? Yeah, so we need an initial angle. Okay. I'm just going to call that ang0 for my starting angle. Okay. What angle do we want to throw it at? Give me an angle. 60 degrees. You said 60 first. Okay. So this will be the initial angle, and the units will be degrees. Okay, so it's important to know that's not radians. When we're doing projectile motion, we usually work in degrees. The initial height, let's not make it start on the ground. Let's make it more interesting. Let's start 2 meters off the ground. Now, this isn't the initial position. This is the initial height, right? Now, this is going to be two-dimensional. So wherever I have something for y, I should probably also have what? Something for x. Okay. So since I'm alphabetically inclined, I'll do an x naught is 0. And this will be the initial horizontal position in meters. Evan, you said you have a question? Oh, it's just the capital A and G, and then I put a 0. That's not a theta. They put that strike through so that you don't confuse your O and your 0, because a capital O would look very similar to a 0. Okay. Now we'll worry about the plot in a little bit. We're not actually going to want to plot things versus time. We're going to actually want to plot the actual projectile motion. So the time plot choice will change up later. All right. Okay, so as we're going through things, remember we're doing everything in 2 dimensions now. So we have to basically double everything out. Do we have to double out time though? No, time is time. We don't have a x and y time. We just have time. So we have the length of the time vector. All right. And then f will be, we want to probably take this line of code and we want to double everything. Okay, so I'll copy it. and paste it. Let's do the same thing for acceleration. Copy, paste. Copy, paste. Okay, and then we have the Y, can copy, I'll paste it up here. Okay, so we have 2x, but what do we really want to have? The first one should be fx, okay? And we can choose to shift enter. Okay, and it will change those. Okay, and then the second one should be f of y. Actually, the shift enter probably wasn't all that helpful in this case. Okay, then we need to do, is everybody with me? Okay, let's do the same thing for all of the others. Go x then y on each one. Ax, ay, v, x, v, y, and then x. You don't do yx, just call it x. All right. So now we have force. We're doing faves, force, acceleration, velocity, and position, all of them in both the x and the y direction. Okay, so let me keep going here. Now, are we thumbs up? Is everything initialized? I'll give you a moment to catch up. Okay. So now you can see we have pulled the first value of v for v naught. Oh, we need to be, actually, we're going to need to be careful here. Okay, we no longer have just a v naught. Okay, we're going to want to change something here. Okay, so we have a couple of velocities that we need to worry about, not just the velocity, which we need to worry about. The x and y initial velocities. And remember, for projectile motion, that's where you use your trigonometry. So how do you get this? Remember, it'll be the first one in MATLAB, right? How do we get the initial x velocity? Whoops, and I misspelled it. It's lowercase v naught times cosine. Now, how do you do cosine in degrees in MATLAB? It's a cosine with a d on it. If you don't put the d, right, it will return. Oh, and this will be of ang 0. Okay. If you don't put the cosine d, it'll think it's in radians. That's the default. All right. You definitely don't want that. Okay. Oh, we should use a semicolon. My mistake there. All right. And I'll say this is the x component of launch velocity. Okay. And then we probably want to turn around and do the same thing for Vy, but instead of cosine d, what are we going to use? Okay, so in MATLAB, remember the initial one is the first one. So V0, be careful with capitalization, times, you have to make your variables match exactly. If it doesn't work, you should check for spelling and capitalization first, okay? So this will be the y component of launch velocity. Okay. And then we have x, y1 is y naught. We should probably also, I'll put it before that. I'll keep going x, y. So if I have a y1 being established as y naught, I should probably also have what? x1. So I need an x1, not equal to y naught, but is equal to x naught. So we're translating our physics into MATLAB. Let me just space this a little bit better. Okay, it's just a little easier to read if you put spaces around your equal signs. All right. Now, when we get down to the while loop, we need to still set a counter. All right. And let's ask ourselves, are the while conditions the same? Let's assume we're launching in the air around an infinitely flat surface like the ground. Our logic right now for running the loop is we keep running the loop as long as what is true. What does while yit is greater than equal to 0 mean? Well, it's above the ground, right? Is that the same condition now for a projectile? Yeah, we want to keep looping as long as it's above the ground. And we also have as long as time hasn't run out, okay? So we'll limit ourselves to T max. If you end up stopping before you hit the ground, you just need to make T max bigger, all right? Now we have a different set of code that we can write here, okay? We talked about this yesterday, okay? We can actually, we need f of x and we need f of y, okay? It had changed the f to f of x because I had done shift enter earlier. So remember yesterday in class, so I'm getting rid of all of that about f. Right. So we're going to have to figure out what f of x it is. Okay. Remember yesterday, we talked about that it was the opposite of b. It was the opposite of the direction of vx. Okay. And we multiplied by b, but we also had to multiply by the magnitude of the velocity vector. So since it's going to show up twice, I'm going to actually put in a v of, okay, v in this loop. It's not a vector. It's not something we're going to store, so we can use it and reevaluate it every time through the loop. Okay, this will be the square root of vx of it squared. That's the it that we're on, plus vy it squared. Okay, and I believe it automatically gave me the right number of brackets. So let's talk about what this is. This is the magnitude of the velocity in the present time. Oh, I put my square in the wrong place. That I'm not squaring my it. I'm squaring after that. Okay, so focus on this line of code. This line of code is it's the square root of the sum of the squares of the components. Yeah, so that will be the speed. Okay, and notice it contains both x and y, right? Now in the x direction, we had yesterday said we'll get negative b times vx, but remember it's for this time through the loop, so vx of it. We want a particular v, okay? If we just do vx, it'll give me all 100 or 1,000 of them. And then now that I've calculated v, I can just multiply that time, whoops, let me go back, times the v value that I just calculated. Okay, so yesterday we had written v of x times the square root of vx squared plus vy squared. Since we defined v to be that second thing, we can shorten up our equation and do that. Any questions on that? So notice if vx is positive, f of x will be negative. Everything else in there is a positive number. Okay. Then we can do the same thing. In fact, since when you do the same thing, it's often good to copy and paste. But if we don't want f of x again, we want now f of y. Okay. And instead of vx, I'll want vy. Now, is that the total force in the y direction? What else acts in the y direction besides air resistance? Gravity. So what else has to act in the, I need gravity in there. What is the force of gravity? How do you calculate it? M times G. Okay, so the force of gravity will be given by M times G. So we're going to, and it is downward, right? So what do I need? Do I add it or subtract it? Subtract it, minus M times G. Okay, because up is positive, so this will subtract. So we have a downward force of gravity. And now, even though this is negative here, it doesn't necessarily mean F of y that part will be negative. When V of y is positive, when we're going up, the air resistance will be down. But when V of y is negative, that means when we're moving down, the air resistance will be up. So we're always going to have the negative of the velocity, the y component of the velocity. Okay, so that gives me my x and y components of force. Okay, then think faves. Let's just do one space between each level of faves here. Okay, so next comes acceleration. Okay, instead of just one acceleration, what do I probably want to have? Instead of a, I want ax. Okay, and that will be f of x of it divided by m. All right, and then right under that, this is, whoop, let me copy it exactly. Copy. Okay, so right underneath of that, whoop, let me tab that in. There we go. Instead of ax again, I want that to be a y. This is the easy part. The force was the thing that's tricky. That's what's unique to this situation. We can always, now we can just get each component of a by taking the appropriate component of x and dividing by m. So we just use f over m in both directions. Okay. The same thing's going to be true with these next couple of steps. Okay. I have velocity, but I'm going to want to do it twice. Let me just copy this line of velocity. Tab in and paste it. So it looks like it's happening twice, but what should the first one be? That should be Vx. Okay. And this will be Vx. You need to put x components on everything. dt is just dt. And then in the next line down, you need to put y's wherever you had a v or an a. So those should now be the y components. All right. Now continuing on, okay, we now have this line about y. Let me copy that. And paste it down. Okay, but let's change the first one into what? X. The top one will be X. We'll keep X on top the whole time. And then this will be V of X. You no longer have V's, we have V of X's. What was? Ah, okay, so he's, I mean, it is the evening math help one. Yes. Let me shrink this for a moment. We have a student joining us. Screen sharing is, let me stop the share. And I will set this up so there's no waiting room, so Ashish should be able to join us as soon as he arrives. All right, so let me go back to the share. Uh-oh. Oh, yeah, there we go. Desktop. Hold on 1 second. Okay. Let me try sharing the desktop, see if that works. Okay, there we are. Okay, so now we have the y of it plus 1. Okay, so we have all of faves programmed in. Okay, now what I want to do, I'm going to run this and see if it actually crashes.
For 152.
Oh, yes, yes. I got interrupted there. We need to make these y components. Okay, now these are y components. All right, and I believe if we run this, whoops, I need to change the folder. And shockingly, it actually worked. Okay, so no, it doesn't like something. I forgot some semicolons, I think, but that's what it is. It says yep. Oh, and a nice thing here, if you forget, it suggests that you put the semicolon in. I can let it do it for me. I have a nice green check there. I should have been looking for that before I ran it. And now it runs. The only thing it does is it doesn't plot what I want. Okay. Right now, it's on plot choice 1, which is position time. Okay. I actually don't want any of these plot choices. What I want to do is I want to plot the X position versus the Y position. Okay. I want to plot X versus Y instead of position time. Okay. So let's get rid of plot choice because I'm not interested in plotting any of those. So since I got rid of all of those, what should I probably do down here? Let's get rid of the switch. I'm going to leave one. I'm going to just use this because we're going to edit this. Control cut. I'll put it up here so we don't have to start from scratch. Okay. So it's okay. We can I'm going to command I or control I to get everything aligned. Okay. Now I just have to change a couple things here. All right. I don't want to do Y versus time. I want to do Y versus what? X versus Y. X versus Y. All right. And then we'll do all of that. And it's not from 0 to T max. Oh, I probably want to do this from 0 up to the maximum of what instead of time? Instead of up to the maximum time, I want it to be up to the maximum X value. Okay. So horizontal stuff will now be X instead of time. Okay, so the X label is now horizontal position in meters. Okay, and the Y label is now vertical position in meters. We could actually shorten that down to the word height. Height in meters. What's that? And then we should, yeah, instead of position versus time, we should do plot of 2D motion. Oh, and I should probably use a capital M. Right? So now when we run this, that's kind of what the trajectory should look like. Now it's kind of distorted, right? Because the scaling 20 in the X direction is not the same as 20 in the Y direction. And I think I can, there's a command that works. I don't know if this works on the online MATLAB, but I can use square. Let's see if it takes that. Okay, so you'll notice that now what it's doing is, I believe, did it actually make a square? Yes, okay. It made a square, but the y units and the x units, I believe, are the same now. Okay, so we have a projectile that launched, reached some peak, and hits the ground at some later point. All right, and so the data is now in there. What could I do if I want more precision in the trajectory? What simple thing that we've always done if we want more precision? Yeah, shorten up the time steps. So right now they're a 10th. Let's just make them 100th of a second each. Okay, and there we go. Okay, it changed the graph a little bit. Okay, it's more precise when we make our time steps smaller. Okay, so moving along, how would we use this? All right, I want to just wrap this up in a couple of minutes. If we want to know where it hits the ground, all right, if what's going to be true about the x where it hits the ground? Logically, the x where it hits the ground is what value? It's the largest, right? So if I go down in the command window and I type max x, the number that comes up is the largest x value. That's where I hit the ground. Okay. Now, what if I wanted to find the time it was in the air? We actually have it coded in. There's something in our loop. Okay. Oh, wait, that ended the while. Okay. Oh, right. Okay. So this is saying if the y that we're on is below 0 or equal to 0, that means we did hit the ground. And then the time where we hit the ground is the step before that. Okay. So we could do t underscore hit. And it'll tell me it took about 3.89 seconds to get into the air. What if I wanted to find the peak of the motion? Yeah, let's find y max. I'm going to say t underscore peak is going to equal find where y is equal to, remember that's a double equal sign, the max of y. So I'm finding where y is its maximum, right? And it tells me that's the 155th time. Okay. Now I can do t of 155. Actually, that's not the, I messed up. That shouldn't be called t peak. That should just be an iteration number. Okay. So I can just say 155. T 155 is 1.54. That means it took 1.54 seconds to get to the peak. What if I wanted the x value at the peak? I could type in x of 155. Okay, 155 is the iteration where I hit the peak. So if I type in x 155, I just found where the peak is. Okay, so we'll play around with that a little bit more, but we now have code that will actually allow us to launch something from any initial height to the ground, right? We might get fancier with this code in the day ahead and allow ourselves to lob things up onto cliffs, all right? So we can change the terrain, and that leads to all kinds of interesting conditions for needing to stop, because hitting the ground isn't the only way that you stop if you're trying to throw something up over a cliff. Right? So I will save this code now. It's always good to hit save at the end of it. And I am going to end the Zoom share. And everyone should watch the video who was not here in class. I will post the video in this week's work. I'll go back to that in just a moment. Okay. Let me pause the recording. Stop.